these earbuds, and I just want to make sure that they work. Is somebody gonna say something? Can you hear me?
We can hear you, Professor.
Thank you. All right, somebody said that he can hear me, but don't have a mic. Benjamin. Okay. All right. Now that I recovered my voice, we'll be able to do a lecture. Let me wait for a few more minutes if there's anybody else coming in. We are missing one person. I might as well actually start. Let's see, since there's a missing person. Oh no, everybody's here. Very good. Let's see. What do I need to do first? Screen share. Share screen. Allow. All right, multiple screens. That is good, and moving out. That is fine. All right. I did put the second test assignment. It's again a mini project, but not extremely challenging. It could be somewhat tedious, and for such a simple problem, you may question whether it is appropriate to pose this because it's tedious to implement, that you could have solved the same thing by hand, which you actually did in the first test. So basically what I'm assigning you to do now is to solve the same problem that you solved in the first test. Without this constraint, that's relatively easy. I don't think that will create much of a confusion. So let's simplify it and just do the strength criteria. But solve it using integer linear programming. And knowing that the strength constraint, psi hill, is nonlinear in terms of these design variables that we're going to use, the number of plies, integer number of plies that we're going to have. With this iterative scheme, well, the scheme will become an iterative because we are linearizing with respect to the number of plies, m and n, and solving the problem. If you solve it with the linearized version, there is a chance that actually the solution will not satisfy the actual constraints. It will satisfy the linearized constraints, but may not necessarily satisfy the nonlinear constraints. That would mean that at the final solution point that you obtained, you're going to linearize it again and solve it as a linear programming problem, checking it again to see if it satisfies the constraints or not. And if it doesn't, you do it again. So there's some tediousness in this, but it's an algorithmic thing that one can actually put all of those into a nice little algorithm, and it will do it in one step. It will give you the final design, as opposed to manually iterating yourself by changing the m and n in the design space. That is what you did for the test one part one. So you're going to repeat the test one part one by using integer linear programming, but you're going to emulate the iterative part by re-linearizing yourself. So the amount of time given for this, assuming that I put this assignment on Blackboard today, I am giving 2 weeks. So that takes us to April 6th, which is the deadline for this homework problem. Any questions? So far, I don't see questions. That's very good. But nevertheless, I'd like to go over the last tutorial that we were doing. And by the way, that is not available on Blackboard. If you go to Blackboard, course documents, let me put it up for your convenience. This is the Blackboard site. The lectures are updated, the tutorials are updated. The last tutorial that I put there is tutorial 10, Design for Failure Using Sequential Integer Linear Programming, which is the methodology that you're going to be using. And if you want, I can also prepare a template for you for test 2 specifically, so that you don't have to deal with everything in tutorial 10, which basically shows you how to do the steps. And I can actually even divide the problem into small steps that as you start working on, I can give you some guidance on what steps that you need to take. Having said this, there is one part that I would like to develop, and that is graphical representation of the Sahil failure criteria. If there is a volunteer soul that will help me to develop that graphical representation of Sahil, perhaps that soul can get extra credit for the course. And what is needed there is the biggest deal is to be able to differentiate different branches when the tension and compression constraints are implemented. And what I have on for that is basically put an analytical form with a piecewise function, so that you'll write one function, but this will be a piecewise function, and depending on the sign of the stresses, it will plot the appropriate quadrant of the constraint. Right now, each quadrant can have a different curve if the tension and compression strengths are not the same. So that's something that perhaps we can write the Saiwu, which probably would be a little easier, but that's on the table for somebody who would like to do that. So this tutorial I'm going to go over again, but this tutorial uses max strain constraint, and I'll show you what you'll need to do beyond this tutorial 10 for your assignment. That will be actually different. Besides the tutorial, if you go back to lectures, the lectures 10, 11, and 12 are there. Lecture 11 is the sequential integer linear programming for strength design. And lecture 12, I actually started this last class, but I'd like to go over this today again after the tutorial. So I'm going to first do the tutorial on integer linear programming. We have done it, parts of it in the past, but I renamed some of the variables so that they became a little bit more meaningful in terms of the design variable names that I'm using. So that that will prepare you for the second project. Then after finishing that, I'm going to look at the lecture 12, flexural optimization with integer linear variables, integer programming. These are binary variables. It will be binary variables. And then we're going to start a tutorial on this flexural optimization for buckling maximization of a rectangular plate, a rectangular plate under compressive loads that we're going to be designing to maximize the buckling load. So this is the plan for today. Let's go back to the tutorial, and that will be tutorial. Oh, incidentally, look at the programs. I have Composites 2021 version 4. For the second project, you need version 4 because this allows individual plies to have different thicknesses, and in fact, that way, to have a ply thickness that is a continuous variable that I typically use for this. You don't need it for the project to have this specific feature, because you'll see that you'll be able to do it without that. But well, having said that, writing continuous version of the program, it will allow you to actually put variables m and n and develop the equations for some of the quantities that you're going to be using, like in-plane stiffness and strains, mid-plane strains, and principal material direction strains, to be parametrically in terms of m and n that can actually change continuously. But during the optimization, we're going to use integer variables, and derivatives will be available via integer variables for us. So download version 4 because that will be useful, and use that one for the project. Some of the Psi-Hill quantities, Psi-Hill formulation may have changed from the version that you've used. So if you don't get the same results for your strength design because of this minor change in the equations in Psi-Hill, ignore that the Psi-Hill that you're going to use in version 4 is the latest one that I'd like to keep for this project. So with that, let's go to tutorial 10. This is designed for failure using sequential integer linear programming. And I'm going to open it from the version that I have on my computer. So I'm going to move this away and be able to monitor, realize if you say something to me, like a text, I'll be able to see it there. And let me go to tutorial. All right, here it is. So I did upgrade it to a point that I actually renamed and grouped some of the cells. So I'm going to first be loading the composites module. I haven't done so yet. But if you look at the titles, the first group of cells are actually setting up the design problem. I might as well change this. And then do the analysis of the baseline design. This is the design, that is the strength evaluation for the baseline initial design point. Initial design point, I call it the baseline design for this case. Then you need to compute the derivatives at that design. So this cell grouping is for computing the derivatives. Then once I have the derivatives, I can write linear form of the constraints, linearized version of the constraints. And that means I'm ready to start iteration. And I design the layup and look at the result. And if I don't like the result, it's not a matter of liking or not liking, but we know that this is an iterative process, that I solve the problem based on linearized constraints. If the result with the obtained with the linearized constraints satisfies the nonlinear one, it's still a good design, but it's not the final design. So you need to re-linearize with respect to the new point and see if you can find a design better than your last design. And you're going to continue until you cannot find a better design until before your previous designs. So in my case, this gives the story of what's going to happen, but let's not go into that right now. That I will be making after the first solution 3 more iterations to find my design. So let me first upload my module for composites. Let's see, file open recently. This is the version 3. All right. So we'll not do any changes to it other than just click the button, run all the code, the entire code. That completes the purpose. I can get rid of it. If it is loaded, it should respond. Yes, it does respond. It says these are the modules that are to be used. This should have been also plot Sahil envelope should have been between stars because this is not working yet. This is the module that I'd like to actually develop. And then I'll write this Saiwu failure and plot Saiwu envelope by using piecewise functions. All right. Now, setting up the design problem. We know that we're going to pose the problem into minimization of an objective function with some constraints. These are generally nonlinear, and we linearize the problem about this initial point x super 0 by evaluating the function at x0, evaluating all the constraints as nonlinear constraints at x0. So these two will become numerical values available to you. And then we will also evaluate the derivative of the function, objective function, with respect to each of the design variables, evaluated at the initial design point again. And summation from 1 to n is the number of design variables, x minus x0, which is the initial design. So this is going to become the linearized variable. This one does. These are numbers, these are numbers, these are numbers. So you will get linear expressions for these functions that could have been originally nonlinear. Of course, in our case, we're trying to minimize the weight. So the weight becomes a linear function of the thicknesses, where since we're dealing only with the A matrix, we don't differentiate the stacking sequence layers to be in the different places. I set the capital I to be from 1 to whatever the number of distinct design variable the orientation angles are. And I'm making mid-plane symmetric laminates, so I put 2 in here, and thickness of the layers will become the weight. And then I write the generic form for strength constraint, which is this. This is a nonlinear constraint. This is where the nonlinearity is. The linear version of this is this one. So you see, you evaluate this at the initial design point, and you put it here. And then the derivatives of these are the midplane principal material direction strains with respect to the individual design variable orientations. Again, I from 1 to 4. There are typically 2 or 3 or 4 distinct orientation angles. If you're using zeros plus minus 45 and 90s, or zeros plus minus 60s. And then the derivatives of the principal material direction strains are written in terms of the derivatives of the panel midplane strains. And panel midplane strains derivatives are simple multiplication of quantities that will be actually already evaluated to do the constraint on G. So this is the parameterization that we are using in this case. We had material properties. I'm going to skip this rather quickly. U matrix, U vector, wrote this laminate generation subroutine. My initial design, I'm choosing it to be m equals 2, n equals 2. So it has 2 layers of zeros, 2 plus 45s, 2 minus 45s, and 2 90s. It's 90, number of 90s are fixed. I'm not changing those. And this is the midplane here, and this is the symmetric part on there. So I can evaluate the A matrix, and I wrote this module, my A matrix, that actually can take non-integer m and n. But for this case, I will tie m and n, which is the number, to ply thicknesses to send into my A matrix calculator as T vector. This is the same counterpart of this in terms of thicknesses. Okay, so my baseline laminate have only the distinct ply orientations, at 0 degree, plus 45 degree, minus 45 degree, with subscript m for 0 and n for 45, and then 90 degree orientation angle, midplane symmetric. This is the base laminate. Associated thicknesses for this is m times ply thickness for the 0 degree layers, n times ply thickness for the plus 45, n times ply thickness for the minus 45, 2 times ply thickness for the 90, because there are 2 90s before the midplane, and beyond this, it's symmetric, midplane symmetric part, which is symmetric of the first part, 2 ply, n ply, n ply, m ply. Then I call my A matrix. So to check it, this is for 1 and 1, and you can check the rest of it. But this particular formulation will also give me A matrix, which is symbolic. Okay, since m and n don't have to be integers, I can actually get an A matrix which is symbolic in terms of m and n. So as the m and n changes, I get to write A matrix out of this. If you want to see it in matrix form, this is 1, 1, this is 1, 2, and this is 6, 6 term. And you can see A16 and A26 are actually 0 because midplane symmetric and balanced. So I take the A11, A22, A12, A66, simplify them from A mid, and then I put them back into the A matrix. So I have now a simplified version of the A matrix, which in matrix form, it looks a little simpler. As you can see, it is the A11 linear function of M and N, A22 function of M and N, A12 is M and N, A66 is a linear function of M and N. But it can be continuous M and N. That's besides the point. Objective function is simple, just that. If I want the A matrix for 2 and 2, this is my A matrix. And if you look at this in matrix form, you'll see that it is actually quasi-isotropic. This one is equal to this one, and this one has the appropriate relation. So this is for M equals N equals 2, it's a quasi-isotropic laminate. If you want to see what laminate looks like, 2, 2, that is 0, 2 plus 45, 2 minus 45, 2, 92, and mid-plane symmetric. All right, now I'm ready to do the analysis for the baseline design. And I need to do the strain analysis. So my load is defined to be 4,000 and 10,000. 1,000. And this is fixed. In your case, this is parametric. It would be alpha, beta, or whatever. If I want to do the analysis of the baseline design, again, just for demonstration, I show the A matrix value numerically for 2 and 2, but I can actually invert the matrix symbolically with M and N. So I'm going to leave those in there, even though my M and N is known at this base design point. I'm going to do the analysis parametrically so that in the future, if I change M and N, I don't have to come back and evaluate A matrix from scratch, but I just change M and N and use the same one. Mid-plane strains, inverse of the A matrix, does it with the load, which means I can also get the mid-plane strains symbolically, okay? So I don't have to evaluate mid-plane strains. But if I want to see their instantaneous value for M equals 2, N equals 2, these will be the values. Mid-plane strains, epsilon 1, 0, epsilon 2, 0, shear strain 0. And under that given loading, this is the numerical value. But as I said before, this now also works for continuous values of the variable. So if N is not 2, but 1.9999, you can evaluate it, then you can see that actually it's pretty close to these values, yet slightly different. So that means I can actually run mid-plane strain analysis with non-integer values. To develop the constraints, G is P, Q, and R individual layers with different orientations, K. J is running from 1 to 6 for 6 different constraints for max strain failure. In your case, there won't be 6 different values of P. There will be a P value that will correspond to the coefficient of psi Hill for a given ply, and that comes from the equation of the strain criteria. Hold on a second. There's somebody strange walking around the house. Oh, incidentally, I was told that there will be a power shutdown in my neighborhood today, sometime today, for about an hour or so. It didn't happen this morning. So if you lose me suddenly, that would probably mean that they shut the power down. So I don't know when that might happen. Perhaps that's the reason why there are strange people walking around my house. But let's not worry about it and continue for the time being. So in the case of max strain, there's going to be one P for this, one P for this, one P for this, one P for this, and two for this absolute value, one for less than, one for greater than for the negative and plus values. So there will be 6 different P's and Q's, and they are given. Transformation matrix to find the strains based on the midplane strains. Ply level strains will be transformation matrix, which is all 4 transformation matrices are in here. So if I go and take the midplane strains symbolically and multiply by the transformation matrices for each of the plies, I get the midplane strains, and I can get them symbolically. I don't have to use this. Let me cut this out first. You see, I can get them symbolically. It's very long, but each layer strains, principal material direction strains, are now written symbolically in terms of M and N. And you can see that there are M and N products and squares and so on and so forth. And that's the nonlinearity. Okay? There's M square and N square. So it's not linear. Ply principal material direction strains are not linear in terms of M and N. They are nonlinear. They are M squares and N squares. That's why we need the linearization. But if we can evaluate them at any given value of M and N, and this is what you get. This is the strains in the 0 degree ply in the principal material direction. And let me also print here midplane strains so that you can see this one. Compare this with the midplane strains. So 0 degree ply has the same midplane strains as the same values as the midplane strains. Plus 45 degree ply does not. That's this one. Minus 45 degree ply has the same strains as the plus 45, except the shear term has a negative sign. And 90 degree ply has a strain which is similar to this, but 1 and 2, epsilon 1 and epsilon 2 are switched. That first value of is 0.0 minus 0.0003, whereas second value here is minus 0.0003. So everything checks. I have the ply level principal material direction strains. PDM stands for principal material direction strains, whereas midplane is clear. These are midplane strains. Each ply has 6 constraints, and they are given in this form. In your home test project, you need to actually come up with what these P1 through Q1 and R1 is. You will not have 6 constraints for a given ply. You will have only 1. But that equation, that is the P's and Q's and R's, will reflect the true form of the Sahil failure criterion. So you need to figure out what this P1 and P2, Q1 and R1 is. In fact, you can drop the subscript. It'll be P, Q, and R. Just P, Q, and R. In my case, I'm going to continue with 6 constraints for a given ply. So definition of P1 through P6 is from the equations above, P1, P2, P3, P4, P5, P6, P1, P2, P3, P4, P6, and failure P's are P1 through P6. That's these. The Q's and R's similarly. So there's Q1, Q2, Q3, Q4, Q5, Q6, and R1, 0, R2, 0, R3, R4, 0, R5, non-zero, R6. The allowable strains for this problem are given as these numbers. These are my strain allowables. In your case, those would be in terms of stress allowables, your P's and Q's. Those have stress allowables, and you'll use the appropriate stress allowables, but in my case, strain allowables. I'm going to use these values. And my first constraint for 0 degree ply, so I represent this G ply for the 0 degree layer. C1 is the first constraint. G ply for the 0 degree ply, second constraint, G2, C2. These are all the 0 degree ply constraints, 3, 4, and 5, 6. And they are written basically repeatedly, like P1, Q1, R1, P2, Q2, R2. Again, for your case, there will only be one constraint for the 0 degree ply, or 45 or 60, whatever you have. All right, now mine is a lot more complicated in terms of number of constraints, so I'm evaluating those, and they're coming up to be strains in that ply, and these have to be less than 1. So this is less than 1, this is less than 1, so 2 and 2, and these less than 1, less than 1. For the 45 degree plies, I put an F in here. So these 6 terms have F. These are the 45 degree plies. And these are all satisfied. And now minus 45s. Those are good. And 9 degree plies, there's a failure here. 9 degree ply fails due to max strain in the second one was, I forgot whether compression or transverse tension. So this is greater than 1. That means it's failing. But we can use these GL ply and C1 through 6 in linearizing the limit. So what we'll do is I'm also going to define the ply thickness 0 to be 2 times ply thickness times M. So the thicknesses of the plies in my equation here, if I go up to the constraint definition, where was that linear constraint definition? Way above, yeah. Here, these are ply thicknesses, okay? So these are not M and N. This is M times the ply thickness of an individual layer, including the symmetric part. So I'm gonna come back here. Come on. All right. And evaluate the thickness of the 0 degree plies, thickness of the 45, thickness of the minus 45, thickness of the 9 degree plies. These are in terms of M and N, except 9 degree plies is 0.02. That's 4 times the total thickness of the ply. And then the base value is when M is equal to 2 and N is equal to 2. This is the baseline. TZ0, TF0, T minus F0, T90 0 initial design. Means 0 after that is the initial design. Now, before finalizing the linearization, I compute the derivatives. And derivatives are given in terms of this equation expression. And I need the Q-bar matrix and inverse of A. So the Q-bar matrix is basically independent of the M and N, because I do know that it's for a 0 degree ply, and I'm going to be needing one for 45 degree ply, and one for 9 degree ply, and one for minus 45 degree ply. So these matrices, there are 4 matrices here. There are 4 Q-bar matrices. So I can use them in the principal material direction or mid-plane direction by using the Q-bar in here. This is what I will be needing, Q-bar times epsilon naught mid-plane strain. And then I'm going to pre-multiply that with the inverse of the A matrix. And inverse of the A matrix is already symbolic form. I can show you what that is. You know what? This happened to me one more time, as if this thing doesn't exist. But I do know that I actually should have computed up there. Oh, EMCH, small m. So that's in terms of m's and n's and squares. All right. So those are very lengthy expressions, each one. There are 4 of them. And they are completely outrageous in terms of m's and n's, m square n's, and n cubes, and etc. And if I go to the derivative of the mid-plane strain with respect to z, I execute this. This is derivative of the mid-plane strain with respect to z, but I need them evaluated at these values. M goes to 2, n goes to 2. So this is partial mid-plane strain with respect to thickness z, 0 degree ply thickness. Partial mid-plane strain with respect to ply thickness f. Partial mid-plane strain with respect to ply thickness minus f, minus 45. Partial mid-plane strain with respect to the 9 degree ply thickness, evaluated at those values. So these are simple numbers. This is the derivative of epsilon 1 in the 0 degree ply with respect to thickness of the 0 degree ply. This is mid-plane derivative of mid-plane strain along the 0 degree ply direction, which is the x-axis direction with respect to thickness of the 0. And these are derivatives with respect to plus 45, with derivatives with respect to minus 45, and derivative with respect to 90-degree plies. So I don't have to do the 1.99. Then I can go to the derivative of the principal material direction strain in the 0-degree ply with respect to thickness of the zero. Derivative of the principal material direction in the 45-degree ply with respect to the thickness direction, and derivative of the principal material direction strain for the minus 45-degree with respect to the thickness of the 0-degree ply, and partial derivative of the principal material direction strain in the 90-degree ply with respect to 0-degree thickness. Those are these. And then you do the same thing for the derivative with respect to the 45-degree ply thickness variation, minus 45-degree ply thickness variation, and 90-degree thickness variation. I've got 16 different derivative terms. Each has 3 terms in it. Those are these. Now I'm ready to construct the linearization. The linearization requires the base value, which is now already computed and stored in G ply ZC1, and then T minus T0T, P1 times Q1 times that, and R times that. So I'm basically writing this expression, one for each layer K, and each value of this I here, 1 to 4, 0 plus minus 45, 90, and then J's from 1 to 6 for each constraint value. So there are 3 variables, I, J, and K. K is the ply orientation for that constraint. J is the strain constraint component out of 6, and I is the distinct orientation angles. So that means I have to write G1 linearized version. It comes to be actually, as you can see, linear with respect to M, linear with respect to N. G2 is the same. G3 of the 0-degree ply, linear. And then 4, 5, and 6, I put them all in one cell. And I can get rid of this and this. And you can see linear and 0 actually. And then I go to 45-degree ply and write 1, 2, 3, 4, 5, and 6 of them for 6 different. In your case, there will only be 1. And I'm showing only 4. And minus 45-degree ply, they're all linear. And 9-degree ply, they're all linear. Now I'm ready to solve the problem. I combine all the constraints into labeled constraints. G1Z layer minus 1 must be less than or equal to 0. I wrote GZ1L as less than or equal to 1, so the real constraint when you say must be less than or equal to 0, you put the minus 1 from right to left here. G2 linear here, G3 0-degree ply, G4 0-degree ply, G5 0-degree ply, G6 0-degree ply. Then you go to 45-degree ply, G1 45, G2 45, and then you go to minus 45 G1 through G6, and then 9-degree ply, G1L through G1 Gn 6L. So these are all the linearized constraints, and when I execute them all, you see them, they're all linear in MNN, and some say true, which means they are already satisfied. They are the zero ones. So if I look at the constraint, for example, 24, it is already satisfied. I can remove 24. I can remove 23. 22 I cannot remove. So I remove a couple here, and then you see 0 degree ply also doesn't have the 5 and the 6 constraint. So I reduced the number of constraints by 4. So this is my latest set of constraints, all linear, which is back to MNN. And I say find solution, find minimum objective function constraints. M and N's are integers, and M must be greater than equal to N must be greater than equal to 0. And solved. Comes back and tells me that the best laminate has no 45 degree plies and 4 layers of 0. The question is, this guarantees that you found the minimum thickness, which is in this case 0.06, assuming linear constraints. Does this design really satisfy the actual constraints? We don't know that. Do I need to do the analysis for that? Yes. But in general, even if it satisfies the linear constraints, it's not the final design. I made an assumption of linearization. I solved the problem. I need to make sure that what I get is the right thing. So I now linearize the problem with respect to the solution of this and solve it again. And see if I can find a lighter design that satisfies the constraints or not. But I'm going to be doing the analysis of this anyways to construct the next linearization. I need to evaluate the constraints when Mn goes to 4 and N goes to 0, which is this laminate. And it has no 45s. That means I actually need to eliminate any variable, any thickness variation associated with 45s, because they don't exist. If you leave it there, you're gonna get the wrong result. And this is actually what is gonna be demonstrated in the rest of it. So make sure that you get rid of N. There's no N anymore. There's only M that dictates how many zeros are gonna be. The 9 degree, there are only 2 fixed for this problem. So my next linearization will require computing the midplane strains with M equals 4, N equals 0. You can read these things to understand what I'm doing. Then I can get the principal material direction strains by evaluating by multiplying it with the T matrices. T matrices, remember, has the 45s in it. So at the end, here, you're going to get these. If there was a 45 degree ply, these would have been the strains in that ply in that direction, principal material direction. But they don't. They're not there, actually. So I'm not going to use these values for anything. I'm just going to use the ones for zeros and ones for the 9 degree plies. So from the ply midplane strains, I'm going to use just the first one, number 1, and I'm going to use the number 4, 9 degree plies. I will not evaluate the G-ply 45 C1 through C6. I'm not going to evaluate G-ply minus 45 C1 through C6. So these are the actual strains at the new design point. And it satisfies all the strain criteria for the nonlinear design. How about the 9-degree plies? That's going to be the key. And surprisingly, it satisfies all the strains in the 9-degree plies. They're all less than minus 1. Okay. So these actually satisfy, but nevertheless, I'm going to actually relinearize the problem about this point. So now the derivatives come. Again, I do that QB1 and QB4 only with respect to thickness of the zeros and with respect to thickness of the 90s, nothing with respect to 45s. So 45s and minus 45s are completely forgotten. That reduces the also principal material direction derivatives significantly. There are only four sets. And the linear constraints for each layer, these are for the 0-degree plies, and these are for the 9-degree plies derivatives. So my constraints are G1, GZ1, GZ2, GZ3, 4, and as you see, 5 and 6 are 0, already satisfied. And in the 90, again, 5 and 6 are already satisfied, so I already removed those. So there are only 8 linear constraints given in this particular form. All right, let's see now. Then what do? I solve the problem again for a new objective function with n equals 0. So my objective function is only in terms of m. That's the objective function here. Constraints are also in terms of m only. There are no n's in the constraints here. And solve it again. And I get actually 2 plies of zeros. Okay? Amazingly, this is much lighter than the previous design, which had m equals 4, n equals 0. And only has 2 plies. But again, it's solved for linearization, based on linearization. So this design with 2 layers, which is this one, may or may not satisfy the constraints. So I relinearize the problem for m equals 2. And these are the mid-plane strains. These are the principal material direction strains. Again, there's 45 and minus 45, but I will ignore them. The 6 constraints for the 0-degree ply. They satisfy all the constraints. 6 for the 90. Oops, there's a violation. But I'm going to be making a new design anyways, based on this point, linearization. So I establish my linearization again, set up my linear constraints, 6 for the 0-degree ply, 6 for the 9-degree ply, put the constraints into new form, solve for m again. This time I got m equals 3. So now m is equal to 3. This is the limit. Does it satisfy all the constraints? If not, I need to do the linearization again and solve it. Do I? Well, it turns out that I may not. So I get m equals 3, mid-plane strains, fly level strains, zero-degree plies, all satisfied, 9-degree plies. It's violating still, 1.26. So do I rerun the problem by linearizing about this point? I don't have to, because the only variable that I'm designing is m. And what the new problem is going to do is going to increase m equals to 4. And I already know that m equals 4 already satisfies the constraints, because I already got that m equals 4, n equals 0 earlier. So you can either go up and look at the values, or you can look at the values here again one more time, evaluating, and you will find that all these constraints are less than 1, which means they satisfy all the constraints. So the final design is m equals 4, n equals 0, and there are 2 9-degree plies. That's it. That is the tutorial for strain, and this is what you're going to be doing similar to this for the test number 2, but for the problem that you solved in test number 1, which is zeros and plus minus 60s, I believe. So you can have z and plus s minus s as 60s, and one constraint per ply. All right, I'm going to save this. And there was one place that actually A matrix was written with capital MAT, so you may want to either change it, or I'll change the, I'll reload this one into the Blackboard. But besides that, I'm actually going to probably prepare you a template for your test, so that you don't just execute everything that I have in my tutorials. We don't need everything. The solution is going to assume that you know the procedure. You don't have to explain everything like I did. You do your own explanation, not my explanations. Any questions? No? All right. So I did the lecture last time for flexure, but there is also a unique approach for flexure problems where the D matrix terms can be linear in terms of these ply identity variables or stack identity variables that we can define. And they are in lecture 12. I updated the lecture charts a little bit, so these may look slightly different than the version that I showed earlier. So we are going to be dealing with the D matrix terms and equations that govern the bending response of layers. And we have shown that lamination parameters can be defined linearly in terms of these, and we can use the integer linear programming. So for cylindrical bending, that's the simpler case that we can do, is the bending equation in general actually has this particular form, and this is applicable also beyond more than the cylindrical bending, because it has y term as well. This is actually for balanced symmetric laminates under in-plane loads nx super 0, nxy super 0, and y super 0. These are the in-plane loads for a flat configuration, and their values are constant. We're going to assume that their values are defined as constants. The in-plane equations are typically coupled with these things, but for simple problems, we can also show that there are these kinds of problems where if you just want to define the laminate deformation W for a square panel, it takes the form nx, ny, nxy disappeared from this, and the Q is there. You can solve this also by assuming D16 and D26 to be 0. That's the easiest problem that you can solve, assuming those. So buckling and bending problem like this can be solved with this. If you're dealing with, say, frequency of vibration, eigenfrequencies, then the eigenfrequencies again are related to D16 and D26 terms with these m's and n's, where m and n in this case is not applied numbers, but they are the half wave along the length. X is m, and half wave assumed half wave along the y n. So that problem is also can be expressed in this fashion. So these are the type of problems that you will be able to solve and design: frequency of a rectangular panel, or out-of-plane deformation of a rectangular panel, or buckling load of a rectangular panel under compression. They'll all be defined in terms of just these, without coupling with the A matrices, if they are symmetric, mid-plane symmetric. We'll be able to just use equations that involve only the D terms. There are no coupling A terms in these problems. Okay. If that is the case, we can represent these D's in terms of what we'll call flexural lamination parameters. These are V0D, V1D, V2D, V3D, V4D, and this is D11 through D16 and D26. And these expressions, these are the coefficients in terms of material invariance. So if you have a problem in terms of, say, flexural lamination parameter V1D, they can furthermore written in terms of the ply orientation angles in this form, where W1 star is normalized W1D, that is this W1D or V4D, V1D is actually, I represent it as V1D here, and my first normalized pressure parameter W1 is 12 V1D over H cubed, and that is written in terms of the percentage of the K equals from 1 to I. In this case, we will not aggregate the same orientation angles. Each ply or stack of plies will have its own K. So if there are 8 plies, mid-plane symmetric, 4 plies above the laminate, K is from 1 to 4. If there are 16 plies in the total laminate, 8 plies above, 8 plies below, then K goes from 1 to 8, Sk cosine 2 theta K. And when you expand this relation, K can repeat for different plies. And W3 star is normalized in this fashion. And if you draw the W1 and W3 space, this is W3 star, this is W1 star, this is a mistake. This should have been W3 star, this should have been W1 star. Then you get again the Mickey's diagram. And the layups on the border are applied with one orientation angle, plus minus theta. All 0 here, plus minus 45 here. 5 minutes left. Thank you, Edison. Plus minus 45 here, and all 90 here. All these points along the border are layers for W1 star and W3 star of plus minus theta. And any interior point has K more than 1. For I equals 1, again, W1 star is cosine 2 theta, W3 star is cosine 4 theta, giving you the expression along this boundary only. For limits I equals 2, then this will be written as S1 cosine 2 theta 1 plus S2 cosine 2 theta 2. And for W3, it'll be again 2 of those. And they will give you all the points inside this diagram. And 2 orientations is going to be enough. If I write the D matrices in terms of W's, then I get these values. D11 through D66 is now linear in terms of W1 star and W3 star. And that's why I see straight lines in this diagram, because what I'm plotting here is W bar, some displacement or out of plane displacement quantity. And they're actually linear in terms of W1 star and W3 star. So D11, D22, D66 are linear. And furthermore, if I define a ply identity variable for 0 degree ply, and these are binary variables, 0, 90, 45, minus 45, and these are 0, 1 variables, they tell whether a 0 degree ply or a 90 degree ply occupies a true thickness position. And this is what we're going to do as a tutorial next lecture. But if you simplify this, you will see that A matrix and D matrix are both linear in terms of these ply identity variables, 0s and 90s and 45s. And any problem can be cast into this linear form. And what we're going to do as a tutorial is the thickness minimization for buckling, which has this form of lambda critical buckling load. And we're going to try to maximize this. I'll explain this expression one more time when we start the tutorial. And this is going to be the formulation of the problem. So we're going to spend at least 2 lectures going through this tutorial, showing how to do the buckling maximization or thickness minimization for buckling, or buckling maximization for a given thickness. Either way, they are corresponding problems, and we're gonna solve that particular problem starting with next lecture. All right, I said everything I wanted to say, gentlemen. Any questions? Start your tutorial tests. You have 2 weeks, and maybe tomorrow during the help session, you can ask questions if you have any questions about this particular assignment. And Thursday, we'll do the tutorial on buckling problem, linearized with identity variables. All right, then. I'll see you either tomorrow or Thursday. Have a good day.